Okay, so today we'll start about the indicators that we are using in volumetric titration. As I said before, what are indicators? Indicators are compounds, chemical compounds. What are indicators here? Indicators are compounds, right? Usually indicators are organic compounds, but there are inorganic compounds also act as indicators. So indicators are compounds which indicates the end point of a conventional volumetric titration. Okay, what is conventional volumetric titration? In conventional volumetric titration, we use a titrant, and we take the titrant in burette. Okay, we'll take a burette. In burette, we take a solution called titrant. This is one reactant, and in the pipette, we take another reactant. We call that solution as analyte. Okay, we take this pipette solution in conical flask, then we'll add an indicator along with that. We add an indicator, right? Then the analyte and indicator will form one color. If you add the titrant to the analyte, at the end point, okay, the indicator changes the color so that we can find the end point of the titration. This is called volumetric titration. We'll take burette, we'll take pipette, we'll take normal conical flask, and we'll add indicator to the analyte, and we'll titrate. This is called conventional volumetric titration. In conventional volumetric titration, to identify the end point, okay, to indicate the end point, we use some chemical compound called indicators. I repeat, what are indicators? Indicators are compounds which indicates the end point of a conventional volumetric titration. Why I am using the word conventional? Because apart from conventional titration, we also have potentiometric titration, we have conductometric titrations, okay, other titrations also there. So that's why I am using the word conventional volumetric titration, in which we use an indicator. In conventional volumetric titration, we use an indicator. Okay, so what we are going to do in this class is we are going to understand what are the different types of indicators available, okay, and what is the principle behind the change in color of the indicator. Okay, so we are going to understand all these things, right? Now, observe this carefully. Indicators undergoes, observe carefully, indicators undergoes a visible color change. This is very important. You cannot use just like that any substance as an indicator. You cannot use any substance just like as an indicator. Why? What is the speciality about indicator? Indicators should give or should show a visible color change at the end point of a titration. Okay, at the end point, some visible color change should be there. Okay, that's the characteristics of an indicator. Then, now, what are the types of indicators we have? Types of indicators. Yes, in indicator, we normally classify indicators based on the titrations that we perform. For example, if you carry out acid-base titration, suppose you take acid as analyte, base as titrant, okay, then add some indicator, then carry out the titration. It's called acid-base titration. The indicators used in acid-base titration are called acid-base indicators. Then, the indicators used in redox titration, Okay, in redox titration, we use an oxidizing agent, right, as analyte, and we use a reducing agent as titrant. It can even be vice versa. Okay, you can take reducing agent as analyte, oxidizing agent as titrant. Right? Those titrations are called redox titrations. The indicators used in redox titration are called redox indicators. Then we have third type of indicators called adsorption indicators. What are these adsorption indicators? Listen, there are titrations called precipitation titration. Right here. See, acid-base indicators are used in acid-base titration. In acid-base titration, we use either acid or a base as analyte, then base or acid as titrant. Right? Then we do reaction, and those reactions are called acid-base titration. The indicators used in acid-base titration are called acid-base indicators. Then we have reactions called redox reactions or redox titrations, where one reactant is oxidizing agent and the other reactant is reducing agent. We take any one as analyte and the other one as a titrant. Okay, those reactions, titrations are called redox titrations. The indicators used in redox titration are called redox indicators. Then there is a third type called adsorption indicators. Listen, we have a special type of reaction called precipitation titration. Precipitation titration. Okay, this precipitation titration, where one reactant is taken as analyte and the other reactant is taken as a titrant. When you add titrant to the analyte, if you mix them, they react and form a precipitate. We call this type of titration as precipitation titration. Okay, the indicators used in precipitation titrations are actually called as adsorption indicators. Right, then we have the fourth type, which is very special and very important also. Listen, there are reactions called complexometric titrations, right? There are titrations called complexometric titrations, C-O-M-P-E-L-E-X-O, complexometric titration. What is complexometric titration? We take one reactant as metal ion, another reactant as a ligand. One is metal ion, the other one is ligand. Okay, we'll take metal ion as analyte, or we take fourth type of indicator called metallochromic indicators. These indicators are used in complexometric titration. What is complexometric titration? See, we take some metal ion as one reactant and we take ligands as another reactant. Okay, we take metal ion as analyte and ligand as titrant. It can even be vice versa. When you mix them, they form what is called metal ligand complex. Metal ligand complex. Okay, this reaction or this titration is what we call as complexometric titration. The indicators used in complexometric titrations are called metallochromic indicators, also called metal ion indicators. Metal ion indicators. Okay? Right. So, what are metallochromic indicators? Metallochromic indicators are compounds which indicates the end point of a complexometric titration. Yes, it indicates complexometric. Metallochromic indicators are compounds which indicate the end point of a complexometric titration. Okay, listen, I told you already, in volumetric titration, conventional volumetric titration, we always get end point, not equivalence point. Okay, we always get end point. Okay, now metallochromic indicators are also called as metal ion indicators, or they are also called as complexometric indicators. Okay, but this is the common terms we use: metallochromic indicators or metal ion indicators, right? Metallochromic indicators are also called as metal ion indicators. That's all. Metallochromic indicators are capable of forming complex with the metal ion being determined. Observe carefully, very, very important. See, metallochromic indicators are capable of forming a complex with the metal ion. Right? What is meant by this? Listen, I have told you, we take metal ion as one reactant and ligand as another reactant. One is an analyte, the other one is a titrant. If you mix them, they will form metal ligand complex. But before adding titrant to the metal ion, we add metallochromic indicators. So metallochromic indicator, they are capable of forming complex with the metal ion. So first, metal ion form complex with the metallochromic indicator. Okay, before adding titrant, metal ion combine with the metallochromic indicators and form a metal indicator complex. That metal indicator complex has a characteristic color. Okay, so observe carefully. You'll get metal indicator complex. Listen carefully. Metal indicator complex and uncomplexed indicator, also called free indicators. Indicators which are not combined with the metal, called free indicators. Metal indicator complex and uncomplexed indicators have distinctly different color. What is meant by that? Listen, when you add an indicator, metallochromic indicator to the metal ion, okay, the indicator combine with the metal ion and form metal indicator complex. The metal indicator complex has one color, whereas the free indicator, uncomplexed indicator have different color. This is the basis of the color change of the metallochromic indicator at the end point. Okay, take it. I repeat, metal indicator complex and the uncomplexed indicator, meaning free indicators, they have distinctly different color. Okay, this is very, very essential point. You should keep in mind. Okay, whatever metallochromic indicator you use, the metal indicator complex should have one color and the free indicator should have a different color. Right? Then the next essential point is that this is very, very, very important. Listen, whenever a complex is formed, okay, we can find what is called a stability constant. Right? Stability constant is a characteristic of each and every complex. It's a characteristic one. So there is a stability constant for metal indicator complex, and there is a stability constant for metal titrant complex. Titrant is usually ligand, so metal ligand complex. Okay, and listen, in the case of complexometric titration, the metallochromic indicator which form complex with the metal, so you'll get metal indicator complex. Stability constant of metal indicator complex should be less than the metal titrant complex. Then only we can perform complexometric titration. This is very, very, very important. You should keep in mind. Okay, if you want to carry out complexometric titration, right, you must choose an indicator in such a manner that the metal indicator complex, stability constant of metal indicator complex should be less than the stability constant of metal titrant complex. Okay. Before the equivalence point or the end point, okay, let me use the word equivalence point here, but you know very well in volumetric titration we always get the end point. Before the equivalence point, the color of the solution in the conical flask, okay, is due to metal indicator complex. The color is due to metal indicator complex, right? Then at the equivalence point, see, we will be having sufficient amount of ligand, titrant. The titrant molecules decompose the metal indicator complex. Okay, what is titrant actually? In complex symmetric titration, okay, titrant in complex symmetric titration, titrant is usually the ligand. Okay. So at the equivalence point, what will happen? The ligands or the titrant. Titrants are usually chelating ligands. What is chelating ligand? We'll discuss. Right? The titrant decomposes the metal indicator complex. The titrant molecules, when you have at the equivalence point, we have sufficient amount of titrant. The titrant molecule decompose the metal indicator complex, okay, and produce free dye. Dye is nothing but indicator here. Produces free indicator here. I have told you already, metal indicator complex has one color, but the free indicator has a different color. So at the equivalence point, the free indicators are produced. Okay. Since the free indicators have different color, so there is a characteristic color change happen, okay, at the end point of a complex symmetric titration. Okay, this is very important point, keep this in mind. So at the equivalence point, the color of the solution is due to the free indicator. At the equivalence point, the color of the solution is due to free indicator, right? Keep this point in mind. Equivalence point, or the better word is actually end point. Right? The better word is actually end point. At the end point, the color of the solution is due to the free indicators. So I have given a schematic representation of how the titration actually occurs and how the color change happens. See, here M represent metal ion, IN represent the indicator. First indicator combine with the metal and form metal indicator complex. Okay, this metal indicator complex has one color, let it be color X, some color. Okay, then the metal indicator complex, right, at the equivalence point or at the end point, what will happen? The titrant, T represent titrant. Titrant molecules, they are usually ligands. The ligands decompose this metal indicator complex. It will decompose, and so that the metal combine with the titrant and form metal titrant complex, and the indicator become free. The free indicator, okay, which is also present in the same solution, right? The free indicator will give a color which is different from the previous one. If this is X, this should be a different color Y. Okay, so X and Y are different here. Therefore, at the end point, there is a characteristic color change happens. It depends on the characteristic color change, depends on the metal ion, depends on the metallochromic indicator that we use. Okay. Now, I'll give some examples for metallochromic indicators. In metallochromic indicator, we have so many indicators, but I have given few here, just 3 here. There are actually so many. Listen, the first one is eriochrome black tea. Observe carefully, E-R-I-O, eriochrome, C-H-R-O-M-E, eriochrome black tea. This indicator is also called solochrome black. Solochrome black. Okay. Listen, in our laboratory, under volumetric titration, we are going to use this eriochrome black tea indicator. Okay, so you are going to perform this titration in the laboratory anyway, so need not worry. And each metallochromic indicator has a pH range, right? For eriochrome black tea, pH range is 10. Okay, it is 10. Therefore, if you want to use this indicator, you must keep the solution medium as pH equal to 10. Okay, normally we use buffer, so we use buffer of pH 10. Okay, to use this eriochrome black tea indicator, right? And which are all the metal ions can be estimated or can be determined? Magnesium, manganese, zinc, cadmium, calcium, etc. Right? We in our laboratory we use eriochrome black tea indicator to determine the amount of magnesium or zinc or calcium present in a given solution. Right? Then, so this is one indicator, metallochromic indicator. The second example, muroxide, M-U-R-E-X-I-D-E, muroxide. The pH range for muroxide is 6 to 13. And what are the metals we determine? Copper, nickel. Okay, we determine the amount of copper present in the solution. We determine the amount of nickel present in the solution, and where we use muroxide as the indicator. Then we have barium in blue. Barium in blue, whose pH range is 3, and this indicator is very specific for iron 3 metal ions, right? Iron 3 plus. Okay, just like this, we have number of metal ions, metallochromic indicators available. I have given only 3. Now, I'll give you the structure of these indicators, how these indicators look like. Okay, what is the structure? Right? This is the structure of eriochrome black tea and muroxide. See, in eriochrome black tea, we have 2 naphthalene unit. This is a naphthalene unit, and this is another naphthalene unit, and the 2 units are connected through an azo group, diazo, N double bond N group. You know very well, when 2 aromatic rings, this is an aromatic, this is also aromatic, when 2 aromatic rings are connected by an azo group, those compounds will behave like a dye. It shows the characteristic color. Okay, and other substituents are there. This naphthalene has, this unit has one OH group, and this unit has one OH group here. Then here we have SO3 minus Na plus is actually an ionic. See, though the structure has huge organic part, okay, the entire compound is actually ionic, right? It is ionic, SO3 minus and Na plus is there. And there is NO2 group. Okay, all these will give strong color to the indicator. Okay, then second one, muroxide. In muroxide, see, we have 2 rings in which we have 3 carbonyl group in the alternate position, CO, 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 and there are 2 nitrogen atoms, right? In between the 2, these 2 and these 2 carbonyl group. Similar structure is available here. See. Similar structure is available, and the 2 rings are connected through a nitrogen atom. And here we have double bond, here we have single bond, and here we have double bond with O minus. Instead of CO, I have O minus here. So there is a conjugation. See, there is an extended conjugation available. Because of this extended conjugation, muroxide shows characteristic color. Okay, yeah. So this is examples for metallochromic indicators, right? Yeah. So there are plenty of examples available for complex aromatic titration, but to understand, as you are beginners, to understand the complex aromatic titration, I am going to take this particular example called EDTA titration. EDTA titration. EDTA titration. Okay, with some metal ion, right? EDTA titration with say magnesium or zinc. Anyone you can take magnesium. Okay, I'll take this titration as an example, right? So observe carefully here. the magnesium ion Mg2 plus is the metal ion. We take this metal ion solution, we take this aqueous solution of Mg2 plus, right? Mg2 plus in conical flask. Observe carefully. Then we take this EDTA. What is EDTA? EDTA is nothing but ethylene diamine, E for ethylene, D for diamine, right? Ethylene diamine tetra, T means tetra here, and A represent acetic acid. Ethylene diamine tetraacetic acid, and we use EDTA as titrant, but we are not using EDTA as such. What we do is what is EDTA? What is the structure? First I'll give you the structure, then I'll explain. This is an ethylene unit. So I'll take 2CH2 group, ethylene unit, diamine. So there are two nitrogens attached, one with this carbon, diamine. Tetraacetic acid, 2 acetic acid unit with this nitrogen, 2 acetic acid unit with this hydrogen. I can write here acetic acid, CH2, remove one hydrogen and connect it to the nitrogen. CH2, COOH, CH2, COOH, CH2, COOH, then CH2, COOH. This is the structure of ethylene diamine tetraacetic acid. Okay, here we have 4 replaceable hydrogen. All these hydrogen can come out as H plus. So I can write shortly this ligand as H4. There are 4 replaceable hydrogens are available, H4, and the remaining part can be taken simply as H4Y. Okay, H4Y. This is a short representation of EDTA ligand. Right? Listen, this EDTA, ethylene diamine tetraacetic acid, this is actually insoluble in water. Observe carefully. This is insoluble in water. Right? Since it is insoluble in water, it is difficult to titrate with the magnesium ions present in the aqueous solution. Zinc ion present in the aqueous solution is difficult because this is in aqueous, whereas this is insoluble in water, then we cannot use. It's difficult. So what we should do is that we should take the sodium salt, disodium salt of this acid. Okay, let me write this as, we'll take disodium salt of EDTA. Right? What we should do? Replace 2 hydrogen, 2H plus. Any 2H plus. Okay, replace 2H plus. One from here or one from here, whatever it is. Replace 2H plus and put sodium. So you get Na2, H2. We replace 2 hydrogen. Y. This is called disodium salt of EDTA. This is soluble in water. We use this compound as titrant in the EDTA titration of with the metal ions like magnesium, zinc, etc. Right? Take it. So aqueous solution of this Na2 H2Y is used as titrant. This is the titrant. We take this solution in the burette and we take magnesium ion solution in the conical flask. Right? Now is it? Let me show you the next page. So we have burette. In burette we have what is called the aqueous solution of EDTA, disodium salt of EDTA, Na2 H2Y. And in the conical flask, you have taken the aqueous solution of the metal ion, and just for understanding purpose I took magnesium ion. Okay, so we have aqueous solution of magnesium Mg2 plus ion. Okay, now what we should do before titration, we should add few drops of indicator. Listen, for EDTA titration, for magnesium or zinc cations, right, magnesium, zinc, calcium ions, we use a metallochromic indicator called eriochrome black tea. Eriochrome black tea. Okay, add few drops of eriochrome black tea indicator to this solution. The moment you add, right, if you mix the two, listen, I am mixing this eriochrome black tea indicator to the aqueous solution of magnesium ion present in the conical flask. Listen, the moment you add, what will happen? The magnesium ion Mg2 plus, it combined with the eriochrome black tea indicator. Listen, you know the structure of eriochrome black tea indicator. Let me show you once again. This is the structure of eriochrome black tea indicator. Right? See, listen, we actually add buffer of pH 10. Okay, buffer of pH 10. In the basic buffer medium, this H plus comes out as, this hydrogen comes out as H plus, so you'll get O minus. This H plus hydrogen comes out as H plus, this becomes O minus, and we have one more minus here. So this molecule become an anion with a charge 3 minus. Okay, with charge 3 minus. So let me write here. So the indicator now carries 3 minus charge. This is actually free indicator, but when you add the free indicator to the magnesium ions, what will happen? It forms a metal indicator complex. Okay, it forms a metal indicator complex Mg In minus 1. Why minus 1? This is plus 2, this is minus 3. If you add, you will get minus 1 as the net charge. This is the metal indicator complex. So first, metal indicator complex is formed. Metal indicator complex is formed, right? And I have told you the metal indicator complex has or exhibit a characteristic color. Actually, the color of this is wine red. Wine red. Okay, a pale red I can say, or we can say wine red. So the color of the solution in the conical flask before the addition of titrant, is wine red. What is the reason for the wine red? The wine red is due to the metal indicator complex that is formed in the solution. Now what we are going to do, we are going to add the titrant to the solution. Let me write here. See, when you add a titrant, what will happen? You know very well, in aqueous solution, the disodium salt will ionize to give 2Na plus and H2Y2 minus. So now the ligand exists in this form, H2Y2 minus, right, in the solution. And in the conical flask, right, we take the metal ion solution. Just for understanding purpose, I took magnesium as an example. So we take aqueous solution of magnesium ion. We take a definite volume of magnesium ion solution in the conical flask. Then we add some small amount of 2 ml or 3 ml of basic buffer of pH equal to 10. Then we add a metallochromic indicator, that is eriochrome black tea indicator. Eriochrome black tea indicator. So before adding the titrant, this is the titrant. Okay, this ligand is actually a titrant. Before adding the titrant to the conical flask, first the magnesium ion combined with the indicator, the free indicator it is usually denoted as In3 minus. In3 minus. First, magnesium ion, let me write here, Mg2 plus magnesium ion combined with the indicator. Okay, this 2 plus, this 3 minus, if they combine, you get magnesium indicator complex. Now, what is the charge? Plus 2 minus 3. If you add, you get minus 1. This is the net charge. So, initially we get magnesium indicator complex, or what's it called? Metal indicator complex. Okay, and the color of this complex is wine red. So this is what happens before adding the titrant. So the solution in the conical flask appears as wine red. What is the reason for the wine red? The reason is due to metal indicator complex formation. Now, if you add the titrant, what will happen? See, let me write in the next page. Look carefully. If you add the titrant, see, we have magnesium indicator complex. To this, we add the titrant. The titrant contains the ligand, which exists in this form now, H2Y2 minus. Now, what will happen? See this? At the end point or at the equivalence point, this ligand reacts with the magnesium. Actually, first to understand this, listen first, remove the hydrogen as H plus. The Y becomes Y4 minus. Then magnesium indicator complex will decompose. This ligand decompose the complex. So you get magnesium 2 plus and indicator 3 minus. This complex decompose. This happens at the end point or at the equivalence point. Now what will happen? This ligand combine with the magnesium ion and form Mgy complex metal ligand complex or metal titrant complex. Metal titrant complex. And what is the charge? This is plus 2. This is 4 minus. If you add, you get minus 2. Minus 2 is the charge of this metal titrant complex or metal ligand complex. Plus, then we have indicator free ion and 2 H plus is there. 1 H plus combined with this and form H indicator minus 2. Then 1 H plus comes out. So as the reaction progresses, we get metal ligand complex and we get free indicator. We call it as a free indicator. See, before adding titrant, the color of the solution is wine red. It is due to metal indicator complex. After the end point, or at the end point, right, the ligand replaces the indicator. So indicator becomes free. The free indicator, okay, shows blue color. So what happens at the end point? Suddenly wine red becomes red. So we can very easily identify the color change of this reaction. Then one more information, very, very important. Why did we add basic buffer here? What's the reason? The reason is that as the reaction progresses, we get H plus. Remember, this reaction is reversible. So it occurs in the forward direction as well as in the backward direction. Backward direction means the complex decompose and form once again magnesium. Therefore, when the reaction occurs in the reverse direction, more ligand is or more titrant is consumed. Okay, see, whatever amount of magnesium available, that amount of 1:1 complex we actually form. So whatever amount of magnesium, whatever number of magnesium ions available, that many ligands should be added. If you have 100 magnesium ion, 100 ligands should be added. But listen, suppose I have 100 magnesium ion. If I add 100 ligand and all 100 ligand combined with the magnesium form complex. We have already added 100 magnesium ion, 100 ligand, okay. If the complex decompose, once again you will get magnesium ion. Your reaction consumes more and more ligands. for the same amount of magnesium, we will be adding excess amount of the titrate. So you will get large error. So to avoid this, what to do? We should not allow the backward reaction to take place. How to avoid the backward reaction? Very simple. Remove this H plus. Because for the backward reaction to occur, we need this and H plus. Then only backward reaction will occur. How to remove the H plus? Add some base. But remember, if you add a base, the base may also decompose the complex. So instead of base, you should use a basic buffer. Okay, we use a basic buffer of pH equal to 10. What the buffer will do? As and when the H plus is formed, right? As and when the H plus is formed in the reaction, that H plus is taken by the or consumed by the buffer. Okay, therefore the H plus is removed from the reaction. Right? Since the H plus is removed, the reverse reaction does not occur. It occurs only in the forward direction. Okay, yeah. So this is the basic idea. Right? Now listen, what is meant by chelating ligand? I said, I use the word called chelating ligand. Listen, chelating ligands are very special. Why they are special? When metal ions, combine with the chelating ligands, right? It forms a complex. That complex is generally stable. We call the complex as chelating complex or chelate complex. This ligand is chelating ligand. Chelating ligand. When chelating ligand combine with the metal, it forms chelate complex. Chelate complex are generally stable. EDTA is an example for chelating ligand. It is actually called hexadentate ligand. EDTA is actually called hexadentate ligand. Hexa means 6. Okay, hexadentate means a ligand, a single ligand with the metal, it forms 6 bonds. 1, 2, 3, 4, 5, 6. Okay, a single ligand forms 6 bonds with the metal and it looks like a ring structure. Okay, we call this type of ring structure, which is formed by the ligand and metal, as chelate complexes, and the ligands which form chelate complexes are called chelating ligands. Okay, let me draw the structure clearly so that you can understand this. Right? Let me draw the structure with the magnesium ion. Observe carefully. Okay, magnesium ion. Actually, the ligand forms an octahedral complex. The ligand forms an octahedral complex with the magnesium. Okay, so let me draw the EDTA here, EDTA structure. So we have one nitrogen and another nitrogen. They form coordinate covalent bond with the metal, and this is the ethylene structure. CH2, CH2, and there are tetraacetate, right? So one acetate group, let me write here CH2, C double bond O, which form one coordinate covalent bond. Then another CH2, let me draw here, CH2, then C double bond O, which form another coordinate bond with the magnesium. Then a CH2 here, this CH2 combined with the CO, and another CH2, C double bond O, right? Yes, and the charge of this is -2. This is the magnesium EDTA complex structure. Magnesium EDTA complex structure, magnesium titrant complex structure, not indicator. Okay, yes, this is the basic principle behind EDTA titration, right? Take